S.Gangopadhyay, and he will talk about information theoretic quantities from gauge gravity correspondence. Please go ahead.
So, am I audible?
Yes, I can hear you.
Okay. So, thank you, Professor Bergshaw, for announcing the start of this talk. So, first of all, I would like to thank the organizers of this conference for giving me an opportunity to speak here. The title of the talk is, as mentioned, it is Information Theoretic Quantities from Gauge Gravity Correspondence. And the talk would be, a part of the talk would be about the familiar information theoretic quantities that we all know. So it would be a sort of review and pedagogic in some sense. And also a part of the work will be on our work that we have carried out in these papers. And before I start, I would like to thank my collaborators, Ashish Shaha and Saurabh Karar, who have collaborated with me in these works. So I would first like to tell about the plan of my talk. So in the plan of my talk, I shall first be telling you about the motivation of doing such things in the first place. And then I shall briefly discuss the holographic principle, which has been discussed in this conference quite a few times. And then I shall move on to holographic entanglement entropy. And the most important part of my talk will be concerned about the thermodynamical property of entanglement entropy for excited states. And then I shall also discuss about the generalized entanglement temperature and entanglement Smarr relation. And this is something which we have observed in our studies, and we name it as entanglement Smarr relation. And then I shall also briefly talk about holographic complexity, which have been discussed in quite details in some of the lectures today by Ali Naseh and Mohsen Ali Shahiya. And I shall also mention something known as bulk reconstruction. So this will basically be the plan of my talk today. So with this introduction, let me move on to the motivation. So we all know that information theoretic quantities such as entanglement entropy have helped us enormously in understanding the nature of phase transitions in condensed matter physics. And surprising connections have emerged between quantum information theory and gravity. The most surprising part of this connection is the following. Apparently, there should not be any connection, since one side is purely quantum mechanical and without any gravitational degrees of freedom, and the other side is a gravitational theory. So in this sense, the connection between quantum information theory and gravity is quite remarkable. And computation of entanglement entropy of conformal field theories, even for free theory, turns out to be extremely difficult. Let aside interacting conformal field theories. Even for free theory, it is very difficult. And it is at this point that the gauge gravity correspondence, or the so-called ADS-CFT correspondence proposed by Maldacena comes handy, because gauge gravity correspondence gives us a new way of computing the entanglement entropy of conformal field theories from the gravity side. So this is basically the motivation of doing such things in the first place. So I shall also, since I have discussed about entanglement entropy, I shall now also discuss, tell some things, a few words about quantum complexity. So quantum complexity is another important quantity that tells us how difficult it is to go from a reference state psi naught to a final state psi, which is connected by a unitary transformation U. So it is, roughly speaking, complexity is basically the minimum number of gates to obtain the unitary transformation. Now, the meaning of complexity in the context of field theory is not quite clear, although there has been a lot of developments recently. And complexity in the holographic sense has also been discussed in the literature. So if I have time at the end of my talk, I shall come to holographic complexity. I shall discuss briefly what holographic complexity is. But for the time being now, let me go on to the holographic principle. So what is holography? A theory of quantum gravity on certain spacetime known as ADS, anti-de Sitter spacetime, is equivalent to a conformally invariant quantum field theory in one less dimension. The reason that this is a profound statement is that quantum gravity, as we all know, is a very difficult subject, whereas quantum field theory, even though it is a difficult subject, we think we have some hold over it. We understand it. What's more is that the duality reduces the number of dimensions. A more complete statement of holography is the following. A theory of quantum gravity in ADS n+1 spacetime is equivalent to an n-dimensional CFT in the n-dimensional Minkowski spacetime that is sitting at the boundary of the ADS spacetime. So this was first observed by Mallasena in this famous paper, The Large N Limit of Superconformal Field Theories and Supergravity. The ADS-CFT correspondence provides a satisfying duality between a black hole in an asymptotically ADS spacetime and a thermal state of a CFT in which the entropy of the black hole is dual to ordinary thermal entropy. But what remains obscure, however, is the relation between the black hole interior and the physics of the conformal field theory. The interior has qualitative features. By interior, I mean the interior of the black hole has qualitative features that one would like to understand from the viewpoint of the CFT. For example, the curvature singularity. So now let me come to the discussion of entanglement entropy, and in particular what holographic entanglement entropy is. So Ryu and Takayanagi proposed how to compute the entanglement entropy for a bipartite system holographically. So for a system consisting of two parts A and B, where B is the complement of A, the entanglement entropy of a subsystem A is the von Neumann entropy and is defined as SA is equal to minus trace of rho A log rho A, where rho A is the density matrix of the subsystem A, which is basically the trace of the total density matrix of the full system, where we have traced over the degrees of freedom of the subsystem B. So once we have the reduced density matrix of the system A, the von Neumann entropy formula gives you the entanglement entropy of the system A. What Ryu and Takayanagi proposed is the following. The entanglement entropy can be calculated holographically by this simple formula. The formula is the following. SA is equal to area of gamma A minimum by 4 Gn, where Gn is the d plus 2-dimensional Newton's constant, and gamma A min is the minimal surface area such that the boundary of this surface is basically the boundary of the subsystem. So what this formula really means will be clear in the next slide. The formula for the holographic entanglement entropy is meant to calculate the entanglement entropy in the field theory side in the large N limit and large U coupling limit, coupling lambda limit. So you can see this diagram. This is the bulk direction, the ADS direction. So this is the ADS d plus 2 space-time, and this is the boundary of the ADS d plus 2 space-time. So this is d plus 1 dimensional, and it is here that the quantum field theory or the more precisely the conformal field theory lives, and also the subsystem A lives in this boundary. Now, what this formula basically says is that on this boundary of the subsystem A, there can be many surfaces that one can have, and one has to take that surface whose surface area is minimal, and that is the Ryu Takayanagi surface. And once you have that minimal that surface whose surface area is minimum, you can basically calculate the area of that surface divided by 4Gn will give you the entropy, the entanglement entropy of this subsystem A. This is what the Takayama formula says, and so this would be really a calculation from the gravity side, because you're using the properties of the bulk space-time, and this is the conjecture of Takayama that once you compute the area of this minimal surface, that would lead to the entanglement entropy of this subsystem A. So now let me move on to another important discussion, which would be the main discussion of my talk, and this would be the thermodynamical property of entanglement entropy. So the first law of thermodynamics reads dE is equal to TdS. It says that when the energy E of a system is increased, its entropy S grows accordingly. Now, since the entropy counts the number of microstates, this is a fundamental law which relates the amount of information included in a system to its total energy. One may wonder if there is an analogous relation for general quantum systems far from equilibrium. A system in thermal equilibrium may be described by energy, temperature, pressure, entropy, chemical potential, etc. Out of equilibrium, these thermodynamical quantities may not be well defined at all. However, one can still compute the entanglement entropy and energy of the system. The interesting question to ask at this stage is the following: is there any relation, analogous relation between entanglement entropy and energy analogous to the first law of thermodynamics? So let us now try to answer this question. An example of a system at 0 temperature is a pure state. One can excite the system, for example, by producing massive particles. It is well known that a good measure of quantum information for a pure state is the entanglement entropy. It would be interesting to know, therefore, how the entanglement entropy for a certain region grows when we increase its energy. Once again, the ADS-CFT correspondence was employed to answer this question, and it was answered in this physical review letters paper by Bhattacharya and Takayanagi. So let us consider an excited state in a d-dimensional conformal field theory. It is assumed that it is almost static and translational invariant. The ADS-CFT correspondence argues that the ground state of this CFT is equivalent to gravity on a d+1 dimensional ADS spacetime. The latter is called the gravity dual of the former. So what one does is one starts with the asymptotically ADS d+1 background, which is of this following form: ds square is r square by z square. So z is the bulk direction, the ADS direction. And times minus fz dt square plus gz dz square, and then you have the other part, and the ADS boundary is z is equal to 0. So near the boundary, one can assume that this function gz that we have here is approximately 1 plus mz to the power of d, where m is a constant. An important assumption in writing this down is that the size of the subsystem, the length of the subsystem, is very small, such that m L to the power of d is much less than 1. What this basically means is the following: if the length of the subsystem is very small, then the surface, the Takayama surface that we have, that protrudes inside the bulk spacetime, which is denoted as gamma A, will be localized near this asymptotically ADS region, and hence one can ignore the infrared region. So here, by the infrared region, we mean the large L limit. In this limit, up to first order in perturbation theory, up to first order in m L to the power of d, one gets the following result. If we apply the Takayama formula, which I have already shown, if we apply this formula here for the spacetime that we are working with now. So if we apply that formula, now we should remember that Gz and Fz, it is given by this form. And if we apply the Ru-Takayanagi formula now, we can holographically calculate the entanglement entropy of the subsystem A, which will be equal to SA naught plus delta SA. And what is SA naught? SA naught or SA this 0 is basically the holographic entanglement entropy of the pure ADS D+1 spacetime. And this SA is the holographic entanglement entropy of this perturbed spacetime. And delta SA measures how much SA is increased in the excited state compared with the ground state of the CFT. So this is a very trivial calculation. One can do the calculation and you will get such an expression for it. Now, the increased amount of energy in the subsystem A can also be computed exactly, and the expression for the increased amount of energy would be given by delta EA is equal to this thing, where it can be computed in a straightforward way, where it is basically the integral, the spatial integral of the TT component of the holographic stress energy tensor. And once you know the form of the holographic stress energy tensor, you compute the TT component of that, integrate it, and that will lead to the increased amount of energy. So what we have now are the expressions for delta SA and delta EA. And therefore, if we just simply take the ratio of these two expressions, we get delta SA by delta EA to be equal to this expression. And we can see that there is this thing is something which is independent of L. This is a pure number. It depends on the space-time, on the dimensionality of space-time. It is a number, and this is proportional to the length of the subsystem. This can now be recast in the following form. It can be recast in a nice form, which is TE delta SA is equal to delta EA, where one can identify TE is said to be the entanglement temperature and is given by this expression. So it is basically the entanglement temperature that we define now is basically it basically goes as the inverse of the subsystem length. So this is the identification that Takayanagi did in his paper, and this relation is analogous to the first law of thermodynamics, although in my viewpoint, this is not really a relation which is analogous to the first law of thermodynamics. The precise reason is very simple. The precise reason is the following, because the reason is that first law of thermodynamics, we know it is a relation in differential form. So dE is equal to TdS. But this relation that we have in terms of the entanglement entropy is not a relation in the differential form. It is rather an integrated form of a relation, and it is not really a differential form. And therefore, it would be a bit. It would not be nice if we really call it to be analogous to the first law of thermodynamics. Rather, it should be called as a relation which is analogous to the integrated form of the first law of thermodynamics, which is basically the Smarr relation in black hole thermodynamics. So now that we have identified the entanglement temperature, now let us take the lapse function. Now let us take the full black hole spacetime, which is Fz is equal to 1 minus z to the power of d by zh to the power of d, where zh is the event horizon of the black hole. Once we take this, so we have this Schwarzschild ADS D+1 spacetime. The Hawking temperature of this black hole can be easily computed, and it is given by this expression. The Bekenstein-Hawking entropy, this is the Hawking temperature, sorry. The Hawking temperature of the black hole reads Th is equal to d by 4 pi zh. The Bekenstein-Hawking entropy can once again be calculated, and the entropy contained in the boundary subsystem volume V, which goes as a capital L to the power of d minus 2 multiplied by the length of the subsystem, that is given by this expression. So we have the expression for this black hole spacetime, we have the expression for the Hawking temperature and the Bekenstein-Hawking entropy. the first law of black hole thermodynamics reads dE is equal to TH ds BH. So there is a typo here. There should be a D here. And once we have this first law of black hole thermodynamics, this leads to the following change in the internal energy due to the thermal deformation of the pure radius d+1 spacetime. So if we just integrate this expression, the above equations basically leads to the following expression. So what we have is now E is equal to d minus 1 by d Th into SBH. So this is the Hawking temperature, Bekenstein-Hawking entropy, and the energy of the black hole. So this is basically known as the Smarr relation in black hole thermodynamics. Now, this is precisely the starting point of our work. This actually motivates us to define something known as a generalized entanglement temperature. So what Ryu and Takayanagi, what Takayanagi and Bhattacharya, they basically defined was an entanglement temperature, which is basically the ratio of delta EA by delta SA. So this was the entanglement temperature that they defined, and furthermore, this was defined in the UV limit, because one should remember that this calculation was done in the UV limit, in the limit of the subsystem size being very small, and in that limit they defined the entanglement temperature. But now what we do is, since we have a Smarr relation for black hole thermodynamics, we define a relation analogous to this relation, and we define what we precisely do is define a generalized entanglement temperature given by this relation. 1 by Tg is equal to d minus 1 by d SREE by E. What is SREE? This is the renormalized entanglement entropy, holographic entanglement entropy, obviously, which is basically equal to SA minus SA0. So we define this generalized entanglement temperature now. We'll see what happens next. This generalized entanglement temperature Tg interpolates between the entanglement temperature in the UV region and the Hawking temperature in the IR region. The expression for delta E in D is equal to 3 spatial dimensions reads of this form. This we can easily calculate if we put D is equal to 3 in the general expression. For SADS4 black hole spacetime, for which D is equal to 3, the renormalized entropy can also be computed, and it reads this. This is the expression for it, where this function Pn is given by this expression. Now, we have the expression for SREE, we have the expression for E. We have everything in place, and if we now naively use, so the important thing is that now we are computing the renormalized holographic entanglement entropy for the full black hole spacetime. We are doing the calculation for the full black hole spacetime, and this is the relation for D is equal to 3. So we are so it is 3 plus the black hole is 3 plus 1 dimensional, and if we do that, what we find is that if we naively use the relation for entanglement temperature, in which the way in which the entanglement temperature was defined. So if we define it now like this, T is equal to E by SREE, and if we now take the infrared limit of this expression, we find that the entanglement temperature comes out to be 2/3 of the Hawking temperature. This clearly shows that the definition in this paper for the entanglement temperature yields the Hawking temperature only up to a multiplicative constant factor in the infrared limit. But we argue that the entanglement temperature that one defines should give you the Hawking temperature exactly, not up to a multiplicative constant factor in the infrared limit. And the reason will be clear as we move on. So now if we do the same calculation by using the definition of the generalized entanglement temperature, Tg in D is equal to 3 spatial dimensions, what we find is 1 by Tg is 2/3 SREE by E. The factor of 2/3 comes from the fact that we should remember that it was D minus 1 by D. So D is now 3, so that gives the 2/3 factor, and therefore 1 by Tg comes out to be 2/3 of 1 by Te. And this implies that in the IR limit, in the infrared limit, that that is the limit when we take L going to infinity, we have the generalized entanglement temperature precisely becomes the Hawking temperature. We can once again do the same thing from our definition of the generalized entanglement temperature. We can apply it for the BTZ black hole also. For BTZ black hole, D is equal to 2, and that would, the factor of D minus 1 by D would then become half. And in case of BTZ black hole, the relation, this entanglement Smarr formula would be something like this: E is equal to half TG SREE. So this factor therefore ensures TG to reproduce the exact Hawking temperature of the BTZ black hole in the IR limit. So the behavior of SREE in the infrared limit, one can calculate it precisely. It is simple calculation. The behavior of TG, the generalized entanglement temperature in the infrared region, that can also be calculated. And similarly, the behaviors in the UV limit can also be computed for SREE and TG, and you can do it for D is equal to 3 spatial dimensions. And as I mentioned, that in case of BTZ black hole, the thermal entropy SBH, change in internal energy E, and the Hawking temperature TH satisfies the following relation. So for the BTZ black hole, the Smarr relation for the BTZ black hole is of this following form, and it is precisely due to this form of the Smarr relation that we can define a generalized entanglement temperature in this form. This was actually first given in Channyong Park's paper, in a PRD paper, with this factor of half. And this factor of half comes out very nicely if we define the generalized entanglement temperature for D plus one-dimensional black hole. The factor of D minus 1 by D gives you precisely this factor of half. And one can now compute SREE for the BTZ black hole, and which is basically SBTZ minus SADS3 in the UV domain, where L by ZH is much less than 1, SREE can be expanded. The relation is of this following form, and using the prescription, once again, the Takayanagi-Bhattacharya prescription, if we calculate the entanglement temperature TE, that will be equal to E by SREE. And in this prescription, one gets, and now if we take the UV limit, one will get TE to be equal to 3 by pi L. And in the IR domain, SRE can be expanded in this form. And once again, using the prescription given by Takayanagi and Bhattacharya in the PRL paper, if we compute it, it will be T is equal to half TH. On the other hand, using the definition of the generalized entanglement temperature, one gets the entanglement temperature to be equal to 6 by pi L instead of 3 by pi L in the UV domain, and TE to be equal to TH, exactly equal to TH in the IR domain of the dual field theory. So this is something very nice. Now I shall go to the discussion of generalized entanglement temperature and entanglement Smarr relation once again, but this time from a different angle. So let me summarize the findings. What we observed, we have observed that in the presence of excitation, a thermodynamic Smarr-like relation corresponding to a generalized entanglement temperature can be holographically obtained for the entanglement entropy of a subsystem. Such a relation emerges naturally by demanding that the generalized entanglement temperature produces the exact Hawking temperature as the leading term in the infrared limit. Remarkably, this relation has the same form as the Smarr relation in black hole thermodynamics. What we now do is we take another example. We demonstrate this for a charged black hole background, which corresponds to a field theory with a finite chemical potential. So let us see how we can do this in this case.
Excuse me, may I ask a question?
Sure.
Yes, it's Dawood. How are you? So
yes, fine.
You know,
yes,
I understand. From what I understand is that the generalized temperature you define is interpolate actually between the UV temperature, which is identified by the entanglement temperature of Takayanagi, and the black hole temperature, which is the IR regime.
Right.
So so okay, that's fine. It's good. So, and you show that actually in the limit, it will be reduced to the black hole and the entanglement temperature. That's correct. But what I don't understand is that when you want to do the calculation, you estimated the metric. You estimated the metric at the UV regime. So you let the Z to goes to tends to 0. So that means that you probe the bulk metric only in the UV regime.
No,
And then no,
no,
it's not like that.
That is precisely the point. What we can do is we can calculate. We have defined the generalized entanglement temperature precisely in that form. What we can do is, let me go back a few slides back. So this is the definition of the generalized entanglement temperature, and it is basically, apart from this prefactor that we have, which depends on the dimensionality of the space-time, it is basically the renormalized holographic entanglement entropy by the energy. And this SREE, now we are calculating it by using the full metric of the space-time. We are not taking any limit from before.
Okay.
So this is how we define the generalized entanglement temperature. We are not taking any limit. The Takayanagi calculation was a calculation where they took the limit L going to 0 limit from before.
Yes.
But we are not doing that. We are keeping it intact, and we shall take the limit, whatever limit, whether it is L going to 0 limit, the UV limit, or the infrared limit at the end of our calculation.
So this linear dependence of the renormalized, what you say, renormalized entanglement entropy, which you subtract the ADS portion from the whole bulk. It has any physical meaning? What it goes like a linear? Can you say something about this? It's very naturally arise, or there is any reason this linear dependence?
Linear
this between SREE and E, between the entanglement and the energy.
I see. Yes. I understand your question. What we are saying is that this 1 by Tg is basically the way in which we define. So we have calculated SREE, and we have E, and we are just taking the ratio of SREE by the energy E, and that we are calling to be the generalized entanglement temperature. So this is a definition to start with this prefactor. And the prefactor, as we shall see later, as I move on subsequently, we shall see that there is a precise reason for choosing this prefactor. This will be clear in a moment. Okay, so let me just carry on. Thank you so much for your questions. So let me come to the case of the charged black hole. So there is a small typo here. The metric of a charged ADS D+1 Reisner-Nordstrom black hole with charge Q dual to a d-dimensional field theory with non-zero chemical potential is of this following form. So this is the standard metric where Fz is the Fz contains this Laplace function contains this charge of the black hole. Now for static charged black holes, the first law of black hole thermodynamics. Now this is precisely the first law of black hole thermodynamics. It reads dm is equal to ph dsbh plus phi dq. So why we call this first law of black hole thermodynamics? Because this is in the differential form, where phi is the electrostatic potential and q represents the total charge. One can now integrate this expression. For ADS planar charged black holes, the above law leads to the following thermodynamic Smarr relation, which is given by this relation. So this is the integrated form, which we call the Smarr relation in black hole thermodynamics. It has also been argued that in order to obtain the internal energy E of the ADS-RN black hole, the contribution of the static electricity part should be subtracted. Therefore, the internal energy E of this d+1 dimensional planar ADS-RN black hole would read E is equal to m minus d minus 1 by d phi of q. So this would be the internal energy of the black hole, and from this formula, the internal energy of the black hole comes out immediately to be of this following form, E to be. So this is once again we are going back. This is the same old formula that I have shown you many times. So E is equal to d minus 1 by d th d sbh. So this is the Smarr relation once again, where sbh and th for this charged black hole are given by these expressions. The renormalized holographic entanglement entropy can be computed easily from the Ryu-Takayanagi formula, and in this case, it is basically the difference between the non-extremal charged black hole minus ADS d+1. It corresponds to the holographic index of non-extremal minus ADS RN black hole. So this is the renormalized holographic entanglement entropy, we now introduce a generalized temperature once again valid for all possible values of the subsystem size L. And we do this in the following form: 1 by Tg is equal to lambda times the ratio of SREE by E, where lambda is a proportionality constant which we shall fix by demanding that Tg is the Hawking temperature of the black hole in the IR limit. Now I come to the justification about this demand that Tg must reproduce the Hawking temperature in the infrared limit. The justification for demanding this condition is quite simple. In the infrared limit, the static minimal surface wraps a portion of the event horizon of the black hole in the bulk, which suggests that Tg must reduce to the Hawking temperature Th of the black hole or the black hole. So what it basically means is that as I increase the length of the subsystem, the bulk, the Ru Takayanagi surface protrudes more inside the bulk spacetime, and in the limit of L going to infinity, the Ru Takayanagi surface now will become basically it will basically reduce to the surface of the event horizon of the black hole. So in the large L limit, what we have is 1 by Tg. If we do the calculations, we will have this expression for the generalized entanglement temperature, and the proportionality constant in this case, if I demand that Tg reduces to the Hawking temperature, the proportionality constant in this case gets fixed to the value lambda is equal to d minus 1 by d. And once the proportionality constant gets fixed, you can simply see that this in turn leads to the following form of the thermodynamics law for the holographic entanglement entropy, which is 1 by Tg is equal to d minus 1 by d SREE by E, which is exactly identical to the Smarr relation in black hole thermodynamics. So from this simple demand, we have shown that the holographic entanglement entropy should obey a Smarr-like relation, which is exactly similar to the Smarr relation in black hole thermodynamics. It is interesting to observe, and once you fix this generalized entanglement temperature, you can now take a UV limit, and you are assured to get the correct entanglement temperature in the UV limit. It is interesting to observe that the entanglement temperature in the UV limit gets a correction due to the presence of the charge parameter in this charged black hole case. However, the leading term here is still independent of the charge parameter, and it depends only on the subsystem size. So with this discussion, let me now move on to the discussion of bulk reconstruction. I still have some time left, so I think I shall finish in time. So let me move on to the discussion of bulk reconstruction. So the entanglement entropy of a 1 plus 1 dimensional CFT on the infinite line is of this following form. It reads, this is the well-known formula that was derived by Calabrese and Cardy long back. So it is SEE function of L is given by C by 3 log of L by A, where C is the central charge representing the degrees of freedom in the CFT, and L denotes the length of the subsystem, and A is the lattice spacing or the UV cutoff introduced in the boundary field theory. And now if we use the Brown-Hanno relation, which relates C to the length of the ADS radius and the Newton's constant, which is 3r by 2gn, we get SEEL to be equal to 2r by 4gn log L by A. Now we carry out the process of bulk reconstruction. What we mean by bulk reconstruction is quite simple. We know the entanglement entropy of the CFT. That is a calculation that has been done independently from the conformal field theory side. And now we want to use the Ru Takayanagi prescription, the holographic prescription, to compute the entanglement entropy of the CFT. So we take an ansatz of the space-time in this following form, and from this ansatz we apply the Ru Takayanagi prescription to compute the entanglement entropy holographically, and then we know the result of the entanglement entropy exactly from the CFT side. We equate the two and try to figure out what these functions fz and hz are. So starting
Excuse
from
me, may I interrupt you? Just
sure.
a simple
Sure.
question. You know, You know, I'm following your
uh,
the E
the
which you say enumerated graphically boundary, right?
I
What you
couldn't
call
follow.
E,
Can you repeat
energy
once
is
more?
calculated. The what you call E is calculated using the stress energy momentum tensor of boundary, right? It's
Right.
integral of T00. But what you call entanglement entropy is calculated from the bulk using the Ryota-Koyanagi proposal.
Yeah.
So
Sure.
the temperature which comes here, the temperature which is the proportionality constant between the entropy, entanglement entropy after renormalization, and the energy is correspond to the which one? It corresponds the quantity in the bulk or boundary.
The energy.
Because when you write the equation, I expect the both side, the right and left, should be calculated from the same frame. I mean, it's
Yeah.
this is boundary. If this, yeah, can you clarify this for me?
Yeah. I will try to clarify your question. So, you are asking a question from the previous discussion. So let me go back to the previous slide. So let me come back. So you are asking something from here, right? And here you see that this energy with which we are dividing, with which we are basically taking the ratio of this SREE is basically nothing but it comes out from TH and SBH, from the black hole quantities. And this is the formula from which you calculate it, right? And then this is the energy, and then you just take the ratio of this energy with SREE to define the generalized entanglement temperature. So I hope this answers your question. So let me just go back to the discussion of the bulk reconstruction once more. So I think I have 9 more minutes left. So now if we take the answers of the bulk space-time to be of this following form, we now apply the Ru-Takayanagi prescription. And for this bulk space-time, the area functional of this geometry would be of this following form, where Z star is basically the turning point and A is the UV cutoff. And if we apply, once we have this area functional, we apply the Ru-Takayanagi proposal. And if we apply the Ru-Takayanagi proposal together with the fact that the entanglement entropy calculated from the CFT side, we use this result now. If we use this result, it would basically lead to an integral equation of this form. So now in place of SEE, what we do, we substitute this expression. And this would, so the left hand side is known, and in the right hand side, there is an unknown function which appears inside the integral, and therefore this is an integral equation. And the nice fact about this complicated looking integral equation is the following, is that it can be solved exactly. The solution for this function f of z is given by this expression, and in the limit a going to 0, in the limit of the UV cutoff going to 0, it gives fz becomes equal to 1. Now we can apply the Einstein field equations to compute what h of z is, and this precisely gives the factor of h of z to be equal to 1, and therefore the space-time that we have now is precisely the ADS, the 2 plus 1 dimensional ADS space-time. And from which, if we compute the holographic entanglement entropy using the Ru-Takayanagi formula, would have given me this Calabrese-Riccardi formula. So in this sense, we have now claimed that we have been able to reconstruct the space-time from the in the holographic way. And this we have done it for the finite temperature case also. The entanglement temperature of the CFT at a finite temperature from field theoretic considerations, it is of this following form. This is also calculated exactly, this has been calculated by Calabrese and Riccardi. The space-time metric that what one gets by using this bulk reconstruction procedure is the usual BTZ black hole, and it is given by this expression. What one does is one follows exactly, one takes an ansatz for the space-time and constructs the area functional, applies the Ru-Takayanagi prescription, equates it with this expression, and gets an integral equation in the unknown function that appears in the metric. And if you solve the integral equation, it would give rise to this space-time for the BTZ black hole. So the observation is that the infrared limit of the HEE gives the Bekenstein-Hawking thermal entropy of a black hole. The open question here that lies here is that, is there really a quantum correction to the Wu-Takayanagi proposal? There has been recently some developments in this related to this question, but it is still an open unsolved question whether there is a quantum correction to the Wu-Takayanagi proposal. Another thing that I would like to stress here is the following. We should, if we have observed carefully, what we have done is we have obtained a Smarr-like relation for the holographic entanglement entropy. So a Smarr-like relation basically means that it is an integrated form of a relation. It is analogous to a Smarr relation of black hole thermodynamics. So the question that lies here is that, is there a differential relation for satisfied by holographic entanglement entropy? Just like the
5 minutes left.
Okay, thank you very much. I will finish in time. So the question is that, is there a differential relation for entanglement, holographic entanglement entropy, which is analogous to the differential the first law of thermodynamics? So this also remains an open question and needs to be investigated further. So before I finish, I would just like to introduce. I would just like to state what holographic complexity is. Since we have already seen a couple of talks before today about what this is, but for the sake of completeness, I shall just briefly review this the idea of complexity, holographic complexity. The observation is the following: the Wu-Takayanagi minimal area naturally gives rise to another unique quantity on the gravity side, and it is nothing but the regularized volume enclosed by the Wu-Takayanagi surface. The conjecture is that the volume must be some form of computational complexity of the state of the conformal field theory. This is the conjecture that was first put forward by Susskind, and there is sufficient reason in believing that the above conjecture is true. It has been argued that the rate of complexification of a CFT in equilibrium scales as Ts by h bar. This is the paper where you can see this argument. And in order to match this rate, the holographic prescription to compute the complexity was given by the following formula, and this is the famous CB conjecture. But there are things, as we have seen in today's talk, there are some issues still with the idea of holographic complexity, and it is really something which is not very well understood as holographic entanglement entropy, in my opinion. And there is a strict mathematical definition of holographic of complexity. So this is the strict mathematical definition I've given in the slide. So it tells us pick a reference state 0, vacuum state, and fix and a fixed finite universal state set of elementary gates, so that an arbitrary unitary operator can be approximated to any desired accuracy by a finite product of elementary gates. We may now define Fk as the set of vectors in the Hilbert space that are obtained by acting on this reference state 0 with a product of k elementary gates, fix a tolerance epsilon greater than 0, and define a metric between two states in this way. This is the Fubini distance between states. The complexity C epsilon of a general state psi is now given by this thing, which states that it is, in other words, this mathematical definition, it tells us that it is basically the smallest number of gates needed to get within a tolerance of epsilon from the given state. So with this I would like to end in my talk. Thank you very much for your attention.
Okay, thanks very much for this nice presentation. So we have time for questions. Are there any questions?
Yeah, this construction of the bulk metric is exact. Yes.
Yes.
I mean, you exactly find, if I give you the program, is that it's like an algorithm. If I give you the entanglement entropy in terms of the entanglement length and the other cutoff, then you can invert these Abel integral equations. Yes. And you can give me the vertex functions.
Right.
Yes. Okay. So what you do with the divergence part? You have some infinity terms there. What are you doing with them? Because when you this, yes,
Yes.
I mean the integral, the original integral Abel integral equation is it doesn't converge. It has a pole, yes, around the turning point z star. So I
Right.
expected some divergence terms. So
Ri-
can you tell me about this?
Okay. So in this case, I have to look back a little bit about the divergence term. I am not I do not remember precisely what would happen to the divergence term, but the thing is that if we start from this and construct the area functional, and we need to just throw away the divergence term. As far as I remember in the calculation, we need to throw away the divergence term. And so in a sense, this entropy that we are working with is see, this expression that you have, that the result that we that has been computed from Calabrese and Cardy, this is also divergent in the a going to 0 limit, right? So it is divergent in the a going to 0 limit. So that is why precisely we have put in the cutoff to avoid the divergence. So this result, if we take the a going to 0 limit, this is divergent. So now if we compute this try to compute the holographic entanglement entropy from this ansatz, from this space-time ansatz that we have taken, we have this UV cutoff over here, right? And this basically blocks the divergence. There is no divergence now because we have the UV cutoff. And if you compute the area functional and equate it to this result that has been computed from the CFT side, which has this cutoff, UV cutoff, that precisely gives rise to an exact solution for this unknown function f of z. And that comes out, it is quite interesting to see that the result for this function f of z contains the UV cutoff. You can see it here. It has the UV cutoff over here. And once you take the UV cutoff going to 0, the UV limit, the a going to 0 limit, you precisely recover the factor of f to be equal to 1. So it is not that you are getting rid of the divergence. The divergence was also there in this result.
You can go through your algorithm to find the.
Yes.
We can go through your algorithm, find the bulk geometry when the boundary theory is just 2 dimensions.
Yes, that's
1 dimension, like it's
right,
like a modular.
Yeah, but for
I
that
think the question we discussed before. Do you think we can probe the bulk?
I think it can be probed, but for that we need to know precisely the expression of the entanglement entropy on the boundary side from an independent calculation.
That's not clear. That's not clear. You understand now proposed one version,
and that's not clear. If one can supply if one can supply this expression, the entanglement entropy on the boundary side from an independent field theory calculation, then I think one can really go for the bulk reconstruction, as we discussed before.
Yeah, that would be very great. But as you mentioned, there is no any unique definitions for the entanglement. Yes.
Right.
Okay, are there any other questions or comments?